Welcome all. Today's topic is organic chemistry 1. That is form 3 work. We have organic chemistry 2, but that we are going to do later. Under organic chemistry 1, you have to know that mostly in this chapter, we are going to tackle the hydrocarbons. Hydrocarbon. And you know that a hydrocarbon is a compound that consisting of carbon and hydrogen. A hydrocarbon is a compound that consists of carbon and hydrogen. In this organic chemistry 1, from the hydrocarbons, they are normally classified into three. Hydrocarbons, they are classified into 3 groups depending on the type of bond that exists between the carbon atoms. These hydrocarbons, they are classified into 3 depending on the number of the bond that exists between the carbon atom. And normally we have the alkane, then alkyne. They are classified into these 3 depending on the type of bond that exists between the carbon atom. If we begin with alkane, know that alkanes are a group of hydrocarbons whose carbon atoms are linked by a single covalent bond. Alkanes are a group of hydrocarbons whose carbon atoms are linked by a single covalent bond. A group of hydrocarbon, that means it consists of hydrogen and carbon, whose the carbon atom are linked by a single covalent bond. We can take the example of the first four, the names and the molecular formula of the first 4 members. So you can let's say name and then the molecular formula. Before that, we have to know the general formula for alkane. The general formula for alkane is CnH2n plus 2. CnH2n plus 2, where N is the number of carbon atom. Number of carbon atom. CnH2n plus 2. If, for example, our first case is methane is CH4. Since N is 1, the number of carbon atom here is 1. 1 times 2, that is still 2. 2 plus 2, 4. That's why we have H4. There's no need to write C1, so it's CH4. If we take the next, is ethane. The number of carbon atom in ethane is 2. So C2, so we have C2. H, 2 times 2, that is 4. 4 plus 2, 6. So we'll have H6. If you talk of the next one, which is propane. C is 3. 3 multiplied by 2, that is 6. 6 plus 2, that is 8. So we have H8. You can take last one as butane. The number of carbon atom here is 4. So 2 times 2, that is, N is 4. 4 times 2, that is 8. 8 plus 2, 10. C4H10. These are examples of the first 4 elements of alkanes. Just take the structural formula whereby you have CnH2n plus 2. After knowing the structure of, you have to remember that the carbon atoms in alkanes are linked by a single covalent bond, therefore forming a group of saturated hydrocarbons. They form saturated hydrocarbons. Saturated hydrocarbons. Because they exist, the carbon atoms are linked by a single covalent bond. And remember that a saturated hydrocarbon is one that contains a maximum number of hydrogen atoms possible bonded to carbon atom. These hydrogen are the maximum possible. That's why we say a saturated solution. After knowing the structure of alkane, we need to diversify and look at the nomenclature. Let's take the nomenclature here. Nomenclature. Nomenclature is a system of naming compounds. So you say this is system of naming compounds. System of naming compounds. Alkanes have names which end with the suffix "ane." The suffix, the end. All the alkanes, we have prefix here, prefix and suffix. All the alkanes, they have the suffix ending as "ane." If we take an example of the first four prefix, the first four is meth, eth, prop, and put. So the suffix is the same. Suffix is same. So it means we'll have methane, ethane, propane, and butane. From this structure, we can say they exist a homologous series, because a homologous series is a group of compounds with similar chemical properties and chemical formula. These alkanes, they have a similar chemical formula and similar chemical compound. That's why we say they exist a homologous series. If we take an example, let's say the series of the first, we can take the first four. So we can have here the number of carbon atoms. We can have here the number of carbon atoms. Then we can have the name. We can have the name. From the name, we can have the molecular formula. Molecular formula. Then lastly, we can have, before that, we can have the structural formula. Structural formula. Then lastly, you can have the condensed structural formula. The condensed structural formula. If we take the number of carbon atoms as 1, if we start with the first one, we can say number 1. So the first alkane is methane. The molecular formula is CH4. So you have written here CH4. Now the structural formula, it means this carbon is bonded by 4 hydrogen. This carbon is bonded by 4 hydrogen. That's why we can have H, then H. This carbon atom is bonded by 4 hydrogen atoms. Then the structural formula still is CH4. That is for the case of the methane. If we take an example of ethane, number 2, you can say here ethane. It means the molecular formula here is C2H6, because you know that the structural formula of alkanes are CnH2n plus 2. You can have here C2H6. It means now 2 carbons atoms are being bonded, 2 carbons. Then the rest will fill up with hydrogens. So you can have here hydrogen, so that we have C2, and also the number of hydrogen is 6. So the condensed structure, we can condense this structure into, you see, this carbon is bonded by 3 hydrogen, 1, 2, 3. So we can say CH3. Then this carbon is bonded by 2 hydrogen, so we can have CH2. Then, this carbon is bonded by also 3, so we have CH3. Lastly, you can have number 3 as propane. Propane, it means we have C3H8. Now we have 3 carbon atoms, 1, 2, 3. So each carbon is bonded by a hydrogen atom. Hydrogen. hydrogen, hydrogen, hydrogen. So we can condense this structure. We can start with CH3. Since this carbon is bonded by 3 hydrogen, this carbon is bonded by 2, so we can have CH2. Also, this carbon is bonded by 3, so we can have CH3. So we can have the condensed structure, and also we can have the structural formula. Those are, I have taken the example of the first 4. As at now, you have looked at brief evaluation of alkane. Want to wind up alkane by looking at isomerisms in alkane. So we want to look at isomerism in alkane. Isomerism in alkane. Alkanes with more than 3 carbon atoms have the ability to form compound with the same molecular formula but different in structure. You see, alkanes with the number of carbon atom more than 3, they have the ability to form an isomer. And we say that isomers, these are compounds with the same molecular formula. They can have, you can say isomers. These are compounds with same molecular formula, but different. Isomers are compounds that have the same molecular formula but different structures. That's why we say that the alkanes, the one with the more than 3 carbon atoms, they have the ability to form an isomer. If we attach from this alkane, if any hydrogen atom is attached from these structures, if there is any hydrogen atom that is attached to the carbon atom, then we derive what we call a branch alkane. Branch alkane. If between these carbon atoms we attach an hydrogen atom, we derive a branch alkane. Then normally there are some rules that we follow when naming the branch alkanes. So we can say rules. When we want to name the branch alkane, there are some rules you have to follow. We can start with number 1. We can say identify the longest continuous carbon chain to determine the name of the parent alkane. Identify the longest continuous carbon chain to determine the name of the parent alkane. So you identify the longest continuous carbon chain. Identify the longest continuous carbon chain. After we have identified the longest continuous carbon chain, then we need to go to the step 2 so that we are able to name this branch of alkane very well. We are told number the longest chain from the end of the chain that is near the branching. Number the longest chain from the end of the chain that is near the branching. What that means, for me to illustrate that, it means I can take an example as, let's say, CH3, CH2, CH3, CH, CH3, CH2, CH3. We need first, like this, we need to determine the longest continuous carbon chain by saying like 1, 2, 3, 4. That means now it will have butane. The last one will have butane. But number 2, we are told number the chain. For us to number the long chain, we number the one that is close to the branch. If we look at this CH3, we can number in 2 ways. If we start from this side, we'll have 1, 2, 3, 4. It means this chain will have number 2. But if we name from this side, we'll have 1, 2, 3, 4. Now, we need to give this branch the simplest number, the shortest number. For this case, now we'll have 2. We'll have 2 methyl. 2 methyl, not 3 methyl. Also, we are saying number the longest chain from the end of the chain that is near the branching. This number 2 is near the branching than number 3. So we give the shortest, the one that's near the branching. That's why we take 2 methyl. And then you can finish, since the carbon atom are 4, so we have there butane. 2 methyl butane. Then there are some instances where we may have more than one branch. Maybe there are 2 branches attached. You can see, in case there are 2 or more similar subsequent groups in the chain, they are indicated by their prefix. E.g., like you can say, we can have di, tri. You may have a case whereby the subsequent groups is attached twice. You can take an example like, say, CH3, 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 CH2, CH3. Like for this case, the methyl group is attached twice. Now, we are not going to use only methyl. We are going to add this di means twice. So we are going to say dimethyl, dimethyl. If there were 3, maybe there's another methyl here, we say trimethyl, trimethyl. Then if it is 4, tetra, as like that. That's all about the alkanes. You have known that alkanes, these are hydrocarbons, which the carbon atoms exist as single bond. Then we have named the structural formula for alkanes, whereby we say that CnH2n plus 2. We look the isomerism and also the naming of the nomenclature of the alkanes. For me to wind up with the alkanes, lastly we can look the laboratory preparation of methane gas. Laboratory preparation of methane gas. Lastly, we can look at the laboratory preparation of methane gas. Laboratory preparation of alkane. You can say of alkanes. You can start with the of alkanes. You can start the first one with the methane. How is methane prepared in the laboratory? Methane. For the case of methane, normally, in general, let's first talk about, before we talk specific, we can talk of general. General preparation of alkane gas. For you to talk of general preparation of alkane gas, we can take, first we can say the formula for alkane, which is CnH2n plus 1. This we can get, this is sodium alkanoate, sodium alkanoate. Then, remember, all the ethanoic components, their suffix is CO. Their suffix is, we can have this as down, CH2n plus 1. And remember that all the ethanoic compounds, their suffix is COO. But since it is sodium alkanoate, this compound, we can take any. Maybe if it was ethanoate, so it will have sodium ethanoate. If it was propane, sodium propanate. Now I'm talking about the general preparation of alkane gas. The general preparation of alkane gas. Then we react with the soda lime. For this case is sodium hydroxide. Whenever you react the sodium alkanate with the soda lime, you'll get the alkane gas, you get the alkane, you get here the alkane. And remember alkane, this is CnH. The formula for alkane is CnH2n plus 2. Then plus sodium carbonate, This is a general formula for the preparation of the alkane. Now, if I take an example of methane, normally for methane, we use sodium ethonate. If you are preparing the methane gas, you use the next compound. From methane, it is ethane. Now you are going to use ethonate. If it was ethane that we are going to prepare, now we use propane. If it was propane, we use butane, the next compound. That's why here, in 1, for methane, we are using ethane. Since we want to prepare methane gas, we add 1, so we are going to use ethane. So here we have sodium ethonate. If it was propane that we are preparing, we could have used now the next one, which is butane, since we are adding 1. Since now we are preparing methane, we are going to use sodium ethonate. We are going to use the sodium ethonate. So the formula for sodium ethonate, CH3COONA, solid, reacting with sodium hydroxide. Now we get the if we are preparing methane gas, now we have CH4 gas. So here, remember here is heating. This is heat plus sodium carbonate, which is solid. That's how we prepare the laboratory preparation of the alkane gas. Lastly, let's look at the chemical properties of alkane. Remember, whenever alkane reacts with oxygen, whenever alkanes react with oxygen, this forms carbon 4 oxide and water. But for the case of methane, we may have where we have sufficient air or limited air. When the air is sufficient, it forms carbon 4 oxide and water. But when air is not sufficient, it forms only carbon 2. But generally, when alkanes react with the oxygen gas, they form carbon 4 oxide and water. I hope that suits the alkane for today. Let's focus on the next chemical properties. The chemical that we have grouped them is alkene. Now we have the alkene. Since we dwell more on alkane, some of the characteristics are going to repeat, but now we are going to move with speed, so that because most of the things we have done in alkane, you have to know that alkene are hydrocarbon which contain at least one double bond. Remember, alkane was single bond, but this alkane, they contain at least one double bond. The first 4 we may have let's say the name and also the molecular formula. The molecular formula. What you have to know, the general formula for alkene is C2H2N. Now you are not going to add 2. For alkane, it was CnH2n plus 2. But for alkene, it's only CnH2n. If we take, let's say, ethyne, C2, 2 times 2, 4. So H4. If it was ethene, this is the double bond. So this is ethene, then propene. Propene, the number of carbon is 3 times 2, so we'll have H6. As like that. Butene, C4, 4 times 2, H8. We just multiply by 2. But for alkane, we are multiplying by 2, then we are adding 2. But for this case, we are only adding we're only multiplying by 2. For the nomenclature, the naming compound is just the same as the alkenes. We are not going to repeat the nomenclature. So let's focus on the isomerism in alkene. The isomerism in alkenes. For this alkene can show two types of isomerism. We have two types. We have the branching isomerism, and also we have the positional. This isomerism. Alkenes can only exhibit the branching and the positional isomerism. If we start with the branching isomerism, we say branching isomerism occurs when a substituent group is attached to one of the carbon atom. So this occurs when the substituent group is attached to one of the carbon atom. Is attached to one of the carbon atom. In the long chain, one of the carbon atom. We can take an example. For example, we can say the butene, put 1 in. For the butene, first the number of carbon atom is 4. So we have C. Since it is double, this is double bond. We put the bond in the first place. This is now put 1 in. Remember, the carbon atom can have only a maximum of 4. So if here is 1, 2, if you put here 2 bond, the bond will be 5. That will be incorrect. The bonds will only be 4, so you have to eliminate 1, so that each carbon must be attached by only 4 bonds. 1, 2, 3, 4. Here we have 1, 2, 3. So we're only going to add 1. Here is 1, 2, so we add 3, 4. 1, 2, 3, 4. Now we can fill the rest with hydrogen. Sorry, it was only that. Hydrogen. Now you can confirm, since butene, the formula is, we just multiply by 2, C4, H will be 8. We can confirm 1, 2, 3, 4, 5, 6, 7, 8. So we have C4, H8. Now we say that branching isomerism occurs when the substituent group is attached to one of the carbon atoms. You see, we can break this carbon atom and attach to one of the, this methyl we can attach to one of the carbon atoms. Like we can say, for example, we can say, let's have here carbon attached to carbon. Then now we can attach that CH3 there. Then now we have here 1. Such that 1, 2, so here we have 3, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So you fill with hydrogen. Such that you can confirm C is 4. 1, 2, 3, 4. Hydrogen is 1, 2, 3, 4, 5. Sorry, this 1, 2, 3, 4, 5. So this bond should not be here. Since each carbon atom must have a maximum of 4, you can confirm 1, 2, 3, 4. So this it was wrong to put here 1. Each carbon must have only 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Such that now the hydrogen we have here is 1, 2, 3, plus 3, 6, 7, 8. So that now still we have C4, H8. But the difference between this and this is that this carbon, we have attached a substituent group of methyl to one of the carbon atom. Like for this case, is carbon number 2. That's why we can say that is a a branching isomerism because one of the carbon atom is the substituent group is attached to one of the carbon atom. Now, if we name this one, this was put one in. But for this case, we first name the methyl group, which is number 2, 1, 2. So we'll have here 2-methyl. Now we'll have but. Now this is not but. Now the carbon atom, now the chain will be 3, 1, 2, 3. The chain will now, we take the chain of the bond, which is 3. Now we'll have prop 2-methyl, prop 1 in. See now the difference between this and this. Since the molecular formula is same, C4H8, but the structure are different. That's why it's an isomerism. And specifically, this is a branching isomerism. This is a branching isomerism. At the branching isomerism, want to look at the next isomerism, which is positional isomerism. Now this isomerism is the word from the word position. It means the position of the double bond in alkene can change. In positional isomerism, can say in positional isomerism, the position of the double bond of the alkene changes. The position of the double bond of the alkene changes. It means, like for this case, this is putene. If we take putene, 1, 2, 3, 4. So the number of hydrogen, the number of bonds will be 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now you can name it as H. So you can confirm if it is C4H8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Now, remember in the first case, when we were tackling the chain, the first isomers, it was the number of carbon atoms attached. The carbon was attached a substituent group. But for this case, it is the position of the double bond that changes. Like for this case, this bond is in carbon number 1. So it means it is put 1 in. This is put 1 in, since it is in the first position. But we can change this position to number 2. We can change it to number 2, such that now we place the double bond in the second position. 1, 2, 3, 4. So here we have hydrogen. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. Now we have 1, 2, 3, 4. 1, 2, 3, 4. Now we can fill the rest with hydrogen. 2, 3. Now for this case, the number of hydrogen is 1, 2, 3. Now we place another one, hydrogen, so that we have 1, 2, 3, 4. For this case, we have 1, 2, 3, 4. So we place here hydrogen. 1, 2, 3, 4. Hydrogen. 1, 2, 3, 4. Such that now we can confirm the number of hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9. It should be 8. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Sorry. Now this now should be only, since 1, 2, 3, 4. If we add another one, it will be 5. So each carbon must have only 4 bond for this case is 1, 2, 3, 4. If we add another one, it will be 5, which is wrong. Now we can confirm 1, 2, 3, 4, 5, 6, 7, 8. Since it is correct, C4H8. But the difference between this and this, we have changed the position of the double bond from number 1 to number 2. So it becomes good 2 in. That's why we have the position isomerism. Now, that's all about the isomerism in alkane. We have the branching isomerism and also the position isomerisms. Lastly, we can talk about the reactions, the reactions that alkanes undergoes. You can say addition reactions. Let's have the addition reactions of alkene. Let's have the addition reaction of alkene. Of alkene. Remember that alkene has a double bond. That's why you have to go additional reaction. It has to undergo some additional reactions. We can start with the first one is halogenation. Remember, halogenation is the addition of halogen atom across a double bond. This is addition of halogen atoms across a double bond. Across a double bond. You can take an example. Let's take for the case of ethene. Remember the structure of ethene. Then we react with bromine gas. If I take from ethene, you can have C2H6 since 2 times 2, so you'll have H4. C2H4 plus bromine gas. Since we have said halogenation is addition of halogen, and bromine is one of the halogen. Remember, it is in periodic table. That is from 2 work. Now, in this case, this one to get the structure it may be difficult, but if you draw this, if you draw the structure, it will become very easy. So let's have the 2 carbons. Since this is a double bond, we put there 2, so it have 1, 2, 3, 4, such that we have 1, 2, 3, 4. So here we have H, then 1, 2, 3, 4, H, such that now we have C2 and H4, 1, 2, 3, 4. This is reacting with the bromine gas. Now you see the structure to form, the structure that will form here. You see this bromine gas will break down this double bond. This bromine gas will break this double bond such that one bromine will occupy this carbon and the other bromine will occupy this carbon. For example, if I break down this like this, if I break down this carbon atom, now for the bond to be complete, there will be 2 spaces, one for here and one here. That means now one bromine will occupy here, another bromine will occupy there. Such that now our structure is going to be, remember that this now just broken down. One bromine will take this and the other bromine will take the other carbons. The rest will remain with hydrogen. 1, 2, 3, 4. 1, 2, 3, 4. Such that now, for you to name this compound, if you are to name, the chain is a day, only two carbon, then a single bond. That is a day. Then bromine is attached, and we can name them. If you start from here, this is bromine number 1, this is 2. So it means we have 1, Then to differentiate the number, we can use a comma. 1, comma, 1, comma, then 2. Since this bromine there are 2, then we can say dichloro. Sorry, dipromo. Now we can say ethane. You see now, with the help of this structure, we are able to name the last part. Now we are going to have the name there, 1,2-dibromoethane. That is halogenation. We may have also chlorine. It does not necessarily to use bromine gas, but the result will still be same. Even if we use another compound, even if we use butane, that structure will break down. Then we'll have there 1,2-dichloro. If it is chlorine, we'll have dichloro. The next addition reaction after halogenation we can talk about is hydrogenations. You can say hydrogenations. Hydrogen gas react with ethene at high temperature in the presence of nickel catalyst to form ethanes. Hydrogen react with alkene to form alkane. Whenever we add hydrogen to alkene, they react to form alkane. For example, if we use ethene, you can say CH2, such that C2H4, double bond. But still, if I write C2H4 is still the same. Meaning I can just say C2H4 plus hydrogen gas in the presence of nickel catalyst. Now we'll have ethane. C. Remember, now this hydrogen now will add to this hydrogen. So we have C2H6. 2 times 2 plus 2. If we're using propene, it will form propane. Butane. That's all about the additional reactions of alkene, and that's all about the alkenes. But lastly, before that, we may have some oxidizing agents. The first case you can use here, you can talk about the oxidizing agent. You can have potassium manganate 7. Potassium manganate 7. Remember, these alkenes are not like alkanes. Alkanes are saturated, but these alkenes, they are unsaturated. It means they can oxidize. For the example of potassium manganate 7, if we add alkene to potassium manganate 7, the purple color disappears. Whenever we add, for example, if it is ethene, if ethene is purple through acidified potassium manganate 7, the purple color turns colorless. Disappears, or you can say here is decolorized or colorless. The purple color. And this one also helpful when you are tackling the practical part of the chemistry. If you are given the manganate 7, then you have seen a decolorized, it is decolorized. Now one of the compounds that is present is alkene. The same with acidified potassium dichromate 7. Acidified potassium dichromate 7. For the case of this, the alkene can turn acidified potassium dichromate 7 from orange to green. From orange to green. That's why we can say this is an oxidizing agent. That's all about the potassium manganate 7 and the acidified potassium dichromate 7. We like to look the last part of this organic chemistry 1, which is alkynes. Let's focus on alkynes. Remember, alkynes are hydrocarbon which contains a triple bond. You can say triple bond. Triple bond. You can take the first three. If it is ethyne, remember the general formula for this is CnH2n minus 2. Remember, for the case of alkene, it was CnH2n plus 2. For the case of alkene, it was CnH2. But for this case, it's CnH2n minus 2. If it is ethyne, it means C2. 2 times 2, 4. 4 minus 2, that comes to 2. Now for the case of ethyne, we'll have C2H2. If it is propine, C3, 3 times 3, 6. Sorry, 3 times 3, 2 times 3, which is 6. 6 minus 2. So we have C3H4. If we talk about butane, C4, 2 times 4, 8. 8 minus 2, so we'll have 6, C4H6. That's some examples of the alkynes. I'm not going to much to dwell on the structure because we have looked under alkane and also we have looked also under the alkene. The same with the isomerism. Isomerism, still we still have the branching isomerism, and also the position isomerism, positional isomerism. Just the case we have done with alkene. The branching isomerism is when the substituent group in the molecule is replaced when we have put the carbon atom in the substituent group. The same with the position is now when the double bond changes, when the triple bond. Now we are talking about the triple bond. I'm not going to focus because we have done it under alkane under alkene. The only thing we're going to do is the laboratory preparation of ethyne gas. Laboratory preparation of alkyne. For the case of alkene, for the sake of ethyne, remember we normally react the calcium carbide plus water. Calcium carbide. So the calcium carbide is CaC2. Calcium carbide is CaC2. Then we react with water, which is liquid. If we are going to prepare the ethyne gas, now we have here the ethyne C2H2 gas, then reacting with the calcium hydroxide plus calcium hydroxides. This is a laboratory preparation of ethyne gas. I'm not going to dwell much on the alkynes since we have tackled much on alkene and alkene, and the most characteristics they're still going to repeat. I would like to end there for the class of today, but next time we are going to do the organic chemistry 2. Still we are going to repeat here because there are some compounds that are still going to under organic chemistry 1. And remember that when these questions are tested in chemistry paper 2, they normally combine both the organic chemistry 1 and organic chemistry 2. They are normally being combined. Just the case of the structure and bonding, periodic table, the chemical formula, they normally combine. The same way here, we combine the organic chemistry 1 and the organic chemistry 2. I hope I'm going to see you in the next class where we are going to do organic chemistry 2. See you.